Okay, for Lab 7, the first problem that we're going to work on is 10.2, number 20. Now for this, we are going to be working on a hypothesis test for a population proportion. So under Stat, we'll open Proportion Stats for one sample, and again, we have summary data. We do not have raw data for this problem, so we say with summary. Now again, we need number of successes, number of observations from the sample that was taken. Now the hypothesis test, remember, we use a historically accepted value. Now in this particular problem, the historical value from December 2001 was 38%. So we want to put in 0.38 as our accepted historical value. And the hypothesis test requires that we decide whether the sample indicates a decrease since this value was collected. So we are testing for a decrease. We want to test whether the real proportion or the current proportion is less than the historical proportion. So we have a left tail test for this. Now, in this particular sample, we had a sample of 1,122 adults, and 403 of them reported that their families ate dinner together 7 nights a week. So we had now 1,122 as our number of observations and 403 as our number of successes. So now we're ready to run our hypothesis test. Now a p-value plot might be interesting, so let's take a look at that just for fun and compute. Now notice we have one of two results showing. This first result shows you the sample proportion. You also now have the z-stat, so if you were using a critical value method, a rejection region or critical region method, you would plot the z-stat against your critical values and see whether you need to reject the null hypothesis. The p-value is also given, so if you choose to use the p-value method, you would compare the p-value with alpha. Now if we click the right arrow, we see the p-value plot. And you notice here what we're seeing is for a left tail test, we see the area beyond the critical value. So the p-value represents the area beyond the critical value in the left tail. And you can see a nice picture of that with the normal distribution. So again, we would save this result and then move on to a new problem. So we save, and then if you need to edit, go back and do that if you realize that you did something wrong. But you should be done with this portion. Now the next problem we'll work on is 10.3, number 24. Now that particular problem does have a data set associated with it, so we'll go to the e-text. Here's the Pearson e-text, and here is, let's see, we're in 10.3. We're going to go over to number 24, and notice we have a StatCrunch link. So we can open with the StatCrunch link and see our data right here. Now for this one, we will be completing a hypothesis test again for the sample mean. So we'll be using t-stats with one sample, and this time we have data. So notice that we'll be selecting the column, filling bottles, and we will be ignoring most of this. Generally speaking, of course, you need to put in the values for the hypothesis test, make your selections there. But generally, you can ignore quite a lot of this stuff. You may want to see a QQ plot. Remember that for small samples, you should do a QQ plot to make sure that you have a normally distributed population. You can also look at the p-value plot, and remember to use the control key if you would like to select more than one of these. Now, I'm going to ignore these for now. Actually, let's see. Oh, I'm not sure how to deselect that, so I think I'll just leave it there and we'll get a probability plot, or excuse me, a p-value plot. Now, for this hypothesis test, we have filling bottles. We use the data. Now, we need our null value for the mean. And so what we see is that the target mean amount of juice is 64.05 ounces. So that is the acceptable value, the accepted value, 64.05. And what we're testing is whether the machine is actually doing that. And so for this particular problem, what they want to know, the quality control manager wishes to verify that the mean amount of juice in each bottle is 64.05 0.05 ounces so that she can be sure the mean is not over or underfilling. Now, what we need to test for is not greater than or less than. We need to test if there's any difference at all, which makes this a two-tailed test. So we're going to select the not equal for the alternative hypothesis, giving us a two-tailed test. And then we can just say compute. Now we have, of course, all of the values here. We have the t-stat, which you would use if you were working with the critical regions. You would use the p-value if you were working with the p-value method and compare that to alpha. And here's the sample mean as well. So what you notice when you look at the sample mean, if you get something like this, for example, now the p-value indicates that we should definitely reject the null hypothesis here. The interesting thing, though, is that since it's a two-tailed test, what you really need to know is whether you are to the left or to the right. Are you overfilling the bottles or are you underfilling the bottles? So the sample mean here is showing to be less than the acceptable mean of 64.05. And so what we actually see is that the machine is underfilling the bottles to a degree that is not acceptable given our tolerances. So the p-value here indicates that the machine really is giving us a statistically significant level of underfilling. So there are a few things important here, and I'll let you go and finish your lab now. Don't forget to save your results and include them in a report. And don't forget to give verbal interpretations as part of your lab report.